Okay, let's have a class, and we first want to just briefly review the Maillard reaction, because some of you not here, and then we're going to go over to talk about meat tenderization. Okay, so we finished talking about Maillard reaction last week. We call it a non-enzymatic browning, and then usually we using a Hodge. Dr. Hodge is a schedule, so we also call it a Hodge Maillard reaction. So what happened is a D-glucose with 3 amino acids. That could be 3 amino acids, could be amino acids in the protein. Then going through, the first step will become N substitute glycosamine. And then we're going through the second step, which is we call it's Amaduri rearrangement. This will generate 1-deoxy 1-amino ketone-thiamine. Ketone-thiamine. And this is we know very clearly, and it happens in a carbon number 1. So I just want to make sure it's correct. 1 amino, 1 deoxy, 1 deoxy, 1 amino ketone-thiamine. Then the things become a little bit complicated. It really depends on the different situation. At the pH relatively acid, 4 to 7, this will happen is 1,2 enolization. And this will generate called hydromethylfurfural, so HMF. At a pH more than 7, which is alkaline environment, they will going through 2,3 enolization. And 2,3 enolization they will generate is reductase or hydroxy reductase. And then if the temperature is very high, and also the pH kind of like an alkaline environment, this will directly generate volatile or fission compounds or fissions. Let's say we had a CH3. This guy comes out. Okay, this is called we call this one is the fission products. This is pyrolyl aldehyde. So that's a fission product. And if we have a reductase right here, the reductase could be directly reacted with the alpha amino acids, and then going through the process, we call it a Strecker degradation. Will generate so-called Strecker aldehyde. And then we're going to go into a later stage, and the later stage has not been very clearly, which means every these compounds that could be working with water, with imine, with other chemicals, and going through polymerization, and also can going through condensation, and will generate a polymer, and that polymer is called melanoidin. Melanoidin. And this is why the Maillard reaction will show you brownish color. And we also say when two enolizations, they generate a brownish color. 2, 3 enolization, usually they generate a very special flavor. Okay, so that's we review the outline of Maillard reaction. So today we want to very briefly introduce you another non-enzymatic browning, which is called caramelization. So I just want to make sure to spell caramelization. This will generate a chemical called caramel. And you know this one. If you order a cup of coffee from a Starbucks, sometimes you want a caramel flavor. So that's called caramelization. So what is caramelization? This is reducing sugar. Now we talk about reducing sugar, which means you need to have a hemiacetal. And the hemiacetal will have a free available aldehyde. So we gave you an example. Sucrose is not a reducing sugar, but glucose, fructose, lactose, maltose, those are all reducing sugar. So reducing sugar without nitrogen compounds and directly become brownish color. And this could be with or without other chemicals such as acid, base solution, or typically with sulfite or ammonium solution. And directly become brownish color, that could be during storage or could be during the heat process. But without nitrogen compounds, which means without like amino acids, without like imine, all those things. Now, our textbook did not mention, Dr. Feynman's textbook briefly mentioned about the 4 different categories. So we call it a class 1 caramel, which is plain. That means without other reagents. So without sulfite and ammonia. And this is typically, I will say, it's a light brownish color usually. Light brownish color, and this is typically is in the coffee-like drinks. Okay, that's a class 1. Class 2 is you are reacted with ammonia, but without sulfite. And this ends up with a pH solution around 3 to 4. So relatively acid. And will generate, we call it a reddish brownish color. Reddish brown. Now, what type of the color is used for the food processing? The beer. The beer color looks like that. And the other alcoholic beverages. But basically it's a beer color, so class 2. Now you know what we're going to say is a class 3, which means they are reacted with sulfite. but without ammonia.
Dr. Chen, I think I have those two confused.
Let me just double check. Sorry, yes, you're correct. So first one is with sulfide. Thank you. I messed it up.
No problem.
Told you not in a good status. I almost want to call today off, but I just think I still can come. Sulfide. Yeah, the first one is with ammonia but without sulfide. The second one is with sulfide,
No.
but without ammonia. Yeah.
No, it's with ammonia, without sulfite.
This is with ammonia without sulfide. That's class 2. Class 3 is with sulfide without ammonia. This is one also, this is generate a dark reddish brown color. This is usually for syrup pudding. The last one, so you can see the order. The class 4, by the way, the second one, the pH is around 4.2 to 4.8. Okay. Last one, with both ammonium and sulfide. That's class 4. And this is, we also generate, we call it a reddish brown color. There is no difference about that. I think there should have some, but to just describe the no difference. What this for is Coca-Cola color. This pH will be a wide range, is 2 to 4. Okay, so these are the 4 different categories for the caramelization. Cola soft drink. Okay, so this is what we finished talk about Maillard reaction and caramelization, about these groups. So the next one, we want to move on to today's topic. We'll talk about the meat tenderization. Dr. Kenny mentioned some of in his lecture, but we were going to be emphasize some new information. Some of them are just review. First of all, we need to know about the meat quality. So meat quality, we talk about with 3 items. Number 1 is we call flavor. Number 2 is juiciness. And number 3 is tenderness. And back in 1996, the American Meat Association did a survey in about the customer in the United States. They find that 39% of the customer will pick flavor as their preference when they're choosing a meat. There is about 11% of the people will choosing juiciness. So you know that when you cook a beef, you want a little bit of juice comes out. You don't want to be very dry. But more than 50% of the customer, they want to pick tenderness as their first choice, as their preference. So we know when we go order a steak in the restaurant, there is a rare, medium rare, well done, very well done. You have a different category. A majority of people will pick like medium well done. Very few people will pick very well done. So that's a tenderness. And there is economic research also find that if you have a 10% increase of tenderness, usually will create more than $130 to $140 million. Well, it's for the meat industry. And the consumers also would love to pay extra $14 for a tenderloin versus a chunk or round. Okay, so that means in the United States, most of the consumers really care about is the tenderness of the beef. Now, how we evaluate a tenderness? There is basically two methods what we can do. The first method is measuring shear force value. We call SFVS value. This could be done with a texture analyzer. And the next Thursday, we'll use Gary's chicken sample. We'll do the shear force value evaluation. The second method, we could do a sensory evaluation. The sensory evaluation could do, number one is consumer type, which means you just pick the person around the campus as a consumer or customer and do the sensory evaluation. Or you could be a trained panel. A trained panel, which means you have to be, let them have a training a couple of times with different juiciness, flavor, tenderness. Then you can have a real evaluation for that. And basically, regardless of the consumer type or trained panel, we always use 9-point, called a hedonic score to do the sensory evaluation. Now, before we do, we need an IRB approve the whole process. So this is something we just want to mention, how we measure the tenderness, shear force value, and also the sensory evaluation. Okay, now, before we talk about the meat tenderization, there is some of the basic knowledge what you should know is the muscle structure. So we want to talk about the second thing is the muscle structure. So let's say there is a muscle, like this. This is the muscle. Now muscle, well, you connected here, to a tender. Then you connected to a bone, okay, to a bone. Then you have so-called blood area, blood vessel. You need to use we call it the artery vein. It's a blood vessel there. Okay. Now we have a muscle. The muscle inside, you will see a lot of like this. I need to draw this a little bit large because it's too small. Now for a whole muscle, there is something packaging it. This is called epimysin on the surface. Okay, then if you took one chunk out, will be like this. This is called a muscle bundle. Then the muscle bundle also packaged with a film, which is called perimysin. And then every muscle bundle, you also composed by a lot of those small units. It's going to go here. Then becomes what? Is a muscle fiber. So become muscle fiber. And we know there is a red fiber and a white fiber So for example, beef had a much higher amount of the red fiber compared to the chicken. Chicken have lots of white fiber. And we also know a sportsman, like I say, athlete, has a huge amount of the red muscle fiber compared to just the normal people. And the film surrounding the muscle fiber, we call it endomyosin. Now, it could be continually to do, later on I'll use different color, continue to do, goes here, this will become a sarcolemma. In the sarcolemma, there is a very special area called sarcolemma reticulum. The acronym is SR. This is a place is release or storage calcium. This related to the muscle contraction and the muscle relaxing. That is a very important structure. And here in the sarcolemma, there is a, we call it a single units of the muscle, which we call it a sarcomere. And then we still can make it very, very thin. Then it will become a myofiber. So we call it a myofibril or myofiber. Okay, myofibril. And then, if you want to still go ahead to cut it, we will become a myofilament. Then we'll be talking about thick filament and the verse thin filament. So if you know the telomere of a muscle, it looks like from outside to inside, it's a membrane bundle structure. And will become every layer inserted with each one and multiple layer and finally become a myofilament. Now we want to talk about, we call it a microstructure of a muscle. We want to talk about this sarcomere, what it looks like. So when we talk about sarcomere, we want to say, let's say this is a sarcomere. Okay? That's one unit. So you're going to draw like this. This is a sarcomere. Just want to make sure the spell is sarcomere. Let's see. It's sarcomere. It should say it's AR. Sarcomere. Okay, that's a single unit. Once you have a sarcomere, that means it is a distance between the Z line. Now, what is a Z line? Z line is a middle line of a band which is called I band. Okay, that's a middle of an I band. What does I means? This I means isotropic. Somehow refraction of light. So sarcomere is a distance between Z line. Now right in the middle, we have another area which is called A band. Okay, why we call it an A band? This A means anisotropic. Then, if we draw a line in the middle of the A band, we'll give you an M line. That's middle line. It's easy to understand. Then the A band inside, you will have a very relatively dark zone. This is called H zone. And inside of H zone, there is another relatively dark zone. This is called pseudo H zone. The function is unknown. Okay, so that's a basic structure. Now, what we really want to talk about is this myofilaments. So, how we do it? We just cut it perpendicular, then we get a sarcomere, and we under the microscope, we could talk about that. So first of all, you will find there is some helix. It's actually alpha helix, like this. I used to draw it really straight, but I draw it like this, okay? What is this called? A relatively thick. This is called thick filament. The thick filament, it is about 16 to 18 nanometer, and this is the length, and the diameter is about 1.5 micrometer diameter. Now, we really interested about is on the thick filament, there is something like that. Like a beam, like a dumbbell, like this. We are really interested about these stuff. Look like a sprouts, you know. You go here. This is called myelin. So that's a thick filament. Okay, now we have a thick filament. And where is the thin filament? The thin filament is usually right in the middle. So they do like this. Usually right in the middle. Right here. Or draw two, okay? This is we call the thin filament. How thin it is? About half size of the thick filament. So about like 6 to 8 nanometer length. And the diameter is 1.0 micrometer diameter. Now, what is the major components on the thin filaments is actin. And we know that eventually they will be cross-linked. Right here, and also right here. If they do contraction, it will be cross-linked. Now, not done yet. When we want to talk about this sarcomere, we talk about the Z line. Surrounding the Z line, there is a lots of the protein. Lots of the protein surrounding the Z line. Some of them, we don't even know the name. But we know some of them. Let's say nebulin, desmin, thymine, etc. etc. There's a lot. So that's our basic structure of that. Okay, now then we want to talk about is just move it. Make sure this is flat. Just turn a little bit. That's good. We can also see that. Okay. So this is a sarcomere. Now we want to talk about is muscle protein. It is very interesting when you talk about a muscle. Majority of them is actually a protein, but there is a different category. 70% is structural protein. 30% is water soluble. And among the 70% of the structural protein, we had 38% is myosin. 13% roughly is actin. And we have left over is some of we call it trypomyosin. This is about left 10%. And there is another called stroma protein, which is about 7%. Okay, there are some others we haven't know yet. A little bit of trace amount. So this is what we talk about muscle protein. Then we want to introduce you a little bit about this myosin. So myosin, we already know 38% of whole muscle protein. It's a huge amount. The molecular weight is very large. How large it is? More than 500,000 delta. It's huge. And we already talk about, I draw like that. The secondary structure is alpha helix. So we know the alpha helix kind of like this, very similar to the DNA double helix. And we talk about there is one term 3.6 amino acids and about 0.54 nanometer. This is we already measured. So 60% is the alpha helix. Then, what are the major amino acids of a myosin? Which is glutamic acids and aspartic acids. And you should know about these things already. If we mention about this a couple of times, the basic structure, we go CH2, CH2. All right, that's glutamic acids. If we go aspartic acids, this will be 1. Okay? So that's glutamic acid and aspartic acids. Now, very important. Relate to the muscle contraction, the tenderization. There is enzyme which can hydrolyze ATP, become ADP, and the phosphate. This phosphate actually could be later on become connected with actin, so the phosphorylated actin, and this needs an enzyme, which is a myosin ATPase, which is an ATP enzyme. And this myosin ATPase is rely on, is a subgroup of myosin, is called merimyosin. Merimyosin has 2 different categories, have large and small. The large is a molecular weight 200,000 delta. Smaller one only 20,000 delta. This one really picky. Only the large merimyosin will have ATPase. Okay, so this is we talk about myosin. Okay, actin. Actin, it's about 13%. So the ratio of myosin and actin is 3:1. This is some of the quiz for the biology. You have some protein, you isolated it, then you weighted the molecular weight. There's a two type of thing. One is 3, another one is 1. Can you guess what type of the protein it is? It could be the muscle protein because myosin and actin, the ratio is 3:1. Okay, what is the major amino acid of actin? Is proline. Okay, proline. If we want to do review, this is, we mentioned, say, this is a circle. So CH2, 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 then combine. So that's actin. Okay, so that's what we have for the actin. Okay, now, sorry, actin, we also have two different type of actin. G-actin, we call it globular actin, and F-actin, fibrous actin. Okay, so that's actin. Now, actin and myosin, they could be connected, cross-linking. Okay. Now, next one. We talk about tenderization. This is like an episode, one by one, one by one. We need to know the muscle contraction versus muscle relaxing. Okay, so what this tells us, the muscle contraction need a neurotransmitter. Acetylcholine. It's a neurotransmitter. Okay, then the acetylcholine, they transfer this one. The signal said, I'm going to do a muscle contraction. So I skip a couple of steps, okay, otherwise it's too complicated. They will go to SR, sarcomere reticulum, which is, we draw the picture there, right here. Then the sarcomere reticulum will release calcium dramatically into sarcomere plasma. And at this moment, there is some assistant protein going to come in, which is called troponin C. The troponin C will assist tropomyosin to showing a place where myosin and the actin can combine, become a cross-linking. They could be combined, become a cross-linking. Now, at the same time, there is something will happen, which means the ATP will be hydrolyzed, become ADP, and phosphorylated actin. This needs an enzyme. We just mentioned myosin ATPase. Now, this phosphoactin, they're going to go back to activate it, to work on a little bit about the myosin actin crosslink. They will break down a little bit. So we call it a breakdown slightly. and then causing sliding of filament. So that is a muscle contraction. The key here is, once you have a muscle contraction, the calcium will be released from the sarcomere reticulum. Okay, now in the opposite direction, we want to talk about the muscle relaxing. At this moment, there is a two theory. One theory said glycine will have some impacts. Okay, our textbook did not mention that, so we don't talk about that. There is an enzyme called acetylcholine esterase. They could break down acetylcholine, which means the neurotransmitter is not there. Once this happened, what will happen? We still talk about the sarcomere reticulum. Instead of the calcium goes back, the release, the calcium goes back. So calcium goes back to the sarcomere reticulum. This troponin C will be blocked to let tropomyosin find the myosin actin to generate cross-linking. They'll go back to the relaxing status. But at the same time, it is very important. The ADP working with phosphate will become ATP generate. And where is this phosphate comes from? Comes from creatine phosphate. So this tells you, in a normal life, if it's a normal cattle, you do muscle relaxing and the contraction, the ATP will be generated, ATP will be hydrolysis, they will be coupled every single second. But what happened is when the cattle has been slaughtered, the blood supply will be depleted, then this coupled action or pathway will be stopped. So, next one we will mention is how the muscle become a meat. And we have this background information for you, then we're going to go back to talk about that. Okay, so first of all, you have, let's say, a cattle. It won't finish to today, okay, maybe need some on Thursday. The other cattle, we will first do a slaughter. Okay, when we do the slaughter, you do killing, which means you kill the cattle. So what happened? Blood depletion. We have a terminology called exsanguization. Okay, once blood depletion, no blood supply there, will become ATP depletion. But here we have to say there is a residue. There is a residue, small amount ATP still there, which is coming from creatine. Very small amount. Once the ATP depletion, what happens? You goes here. The glycogen, usually storage at the liver, that's the only energy resource right now, temporal. The glycogen will going through glycolysis and going coupled with fermentation will generate lactic acids. Okay, once this lactic acid generates, what will happen? The pH will be decreased. So originally, a beef cattle, the pH is about 6.7 to 6.8. Once the lactic acid generates, it will decrease to 5.5 to 5.6. And this comes down to what we talked about before. ISO electronic points equal 5.0. We have to avoid that. If you, in somehow, the pH is decreased dramatically, very close to the PI point, then the contractile muscle will be denatured, the water holding capacity will be dramatically decreased. Okay, so the water holding capacity. Let's go back to that curve. Okay, now this happens, what will happen next? We assuming there is not enough ATP. Okay, we assuming there's not enough ATP. ATP already depletion, or almost non-loaded. Actin, myosin, cross-linking will generate. Because the actin myosin, you break down, you do contraction, relaxing, you need ATP to regenerate. What will happen? A tough muscle. Tough, stiff muscle